Bismillah ar-Rahman ar-Rahim. Alhamdulillah Rabbil Alameen. I just want to talk about flat slopes and pretty much their impact in collection systems and drainage. Um, I will be focusing on, this is going to be really a quick video. This is going to be my first video. It's going to be a dummy video in a sense. Um, I just want to put something out, and let's start with flat slopes. So assume that you have two pipes, pipe number one, pipe number two. The first pipe is the upstream pipe, two is the downstream pipe, and assume that at your downstream pipe you got a flat slope. So flat slopes, we flag them as engineers in water resources, we flag them as a critical flat slope, in a sense that, hey, watch out for this pipe. Now the reason is why. Now you can think of it in like more of like a common sense terms, but I would like to talk about the theory about it, because me personally, I understand stuff based on the theory. Anyways, so pretty much you go back to the basics, like the fundamental equations in fluid mechanics and water resources. The reason a flat slope is critical is due to this. So in your Manning equation, what's your Manning equation? It's V, the velocity, equals 1 over the roughness coefficient multiplied by the hydraulic radius to the power of 2 over 3 multiplied by the slope to the power of 1 over 2. Now, a flat slope means your slope value is small. So what happens is that when you decrease your slope, you are decreasing your velocity. So in your Manning equation, your velocity would end up to be lower. Now from the Manning, we go switch to the continuity equation, which is the flow rate equation. So it states a flow rate is basically volume over time. This is the rate of volume over time. Discharge. So it says that Q equals A1, which is the area, the cross-section area, multiplied by V1, equals A2 multiplied by V2. And in a sense, what it's saying is that your volume is not going to disappear in those two pipes. It needs to keep being conveyed. So what happens is that in the left-hand side of the equation, you have your regular V1 and A1 that are coming from the slope, the upstream pipe that has a regular slope, and it's flowing to your downstream pipe, pipe number 2, that now has a decreased velocity. So what will happen is that your area A2, it will need to increase to account for that decrease, so everything balances out. So from there, your velocity decreases, your area 2 increases, and what that signifies is that the depth of the water in your second pipe is going to increase to allow the same flow rate, to allow the same volume of water to still be conveyed. And yeah, pretty much your depth is going to increase. Now from the continuity, we can move forward to the energy equation, where terms like the hydraulic grade line would come. It will help us understand what's going on, and why it's a critical pipe. So in your energy equation, the total energy equals the elevation head, the pressure head, and the velocity head. Okay, so in open channel, the pressure head is pretty much is simplified to be the depth of the water. So what happens is that in your EGL, your energy grade line, it's still going to be the same, plus the head loss in the second pipe, which is normal. So what happens is that your velocity is going to decrease, and in pipe 2, your velocity is going to decrease and your depth is going to increase. Okay, everything balances out with the with the head loss, obviously. So no biggie in the energy grade line. But now when you move to the hydraulic grade line, which is the key parameter for engineers in like open channel flow, what happens that the hydraulic grade line is pretty much the elevation head plus the pressure head, or like the water depth, in the case of open channel. And the velocity head, the kinetic energy, it's not shown in the hydraulic grade line. So what happens is that V1 plus your water depth Y1 at pipe 1 equals V2 plus your water depth in the second pipe. So since there is no velocity that is being necessarily like decreasing the velocity and increasing the depth, what is showcased is just an increase in the depth. Hence, your hydraulic grade line increases. So generally, that's kind of like what's happening in the equations. I'm sure, like, if we have like a slideshow, like, I have a pen and paper to kind of like show the calculations or whatever, it would make more sense. But this is just kind of me talking about it. So that's that. And generally, in drainage systems, we also have this parameter. It's called the minimum cleansing velocity. So you kind of need a certain value of velocity that will make sure that all of the debris and the waste that is flowing in your drainage system is being cleansed efficiently. So what happens is that if your water is flowing at a really low velocity, this cleansing parameter, like this cleansing phenomena, is not going to be it's not going to be in effect as much. So that's also one of the things that a flat slope does. Since a flat slope signifies a decrease in the velocity, that means that you're more likely to go below this minimum cleansing velocity. And generally, from what I've seen, most standards in the US, they have a minimum cleansing velocity of 2 feet per second. And obviously, with the critical flat slope, other than the fact that it's increasing its hydraulic grade line, it's increasing its water depth, obviously this will also be impacted going below the minimum cleansing velocity, because you have a flat slope. That's that. Yeah.